I am going to talk today on maths and physics of blood pressure part 2. Today I will touch upon some part about the continuation of non-invasive BP and then we'll go to invasive blood pressure monitoring. Some of the things I have already put in my arterial blood pressure monitoring, so it may get repeated. So whenever I talk anything on academics, I put a big salute to the legendary teacher of 2 centuries, Professor Ravi Shankar. Now, what is pulse wave velocity? It is delta x by delta t. What is this distance traveled by time? It can be measured in several ways and in several locations. Now, normal mean pulse wave velocity is distance by delta. Change in the distance by change in time. It moves as fast as this. It is normally 6 meters per second. See here, it starts here. It travels by 6 meters per second. PWD increased with advancing age and BP categories, hypotensis. Now you see if the elastic modulus, if the elasticity is fine, if the vessel wall thickness is good, if the radius is good, the density is fine, yes, it moves. 5-frame rate a model mode ultrasound for calibration of pulseless pressure. There is something called Pyram's solution for this. It consists of an array of sensors integrated into a soft foam band which is worn on the wrist or foot. It sends data wirelessly to a mobile device where continuously BP is monitored in real time. Again, a non-invasive continuous BP monitoring we have discussed in part 1 a few times. This is a detector, this is a movable electrode, a variable capacitance, this is skin. There is photoplethysmography. Devices illuminate the skin and measure volume by the changes in absorptions. Now we'll go to invasive BP. Now there is someone called Stephen Hayes. What he did was he cannulated the carotid artery of a horse and took a big tube like this and found out this was possibly the first invasive BP monitoring. What are the components of invasive BP monitoring? You have put in a line. There are cases. Yeah, there is a first normal saline at 300 millimeters of mercury. Then it comes to a tube to a flow restrictor, which comes with only 4 ml per hour to the artery. It pushes saline at 4 ml per hour when the flow restrictor is acting normally. The pressure there is 300 millimeters. Then only it gives us 4 ml per hour. Catheter may be 20 or 22 gauge parallel sites. It should be PMO lines, pressure monitoring, red, because it is less complex. Compliance means it will be more. That should be a transducer. And then the microprocessors, amplifier, and display. Now you see the arterial line. You can have a sample port. There is the pressure transducer and flushing system, pressure bank, and from key transducer, you have a monitor. This gives 300 millimeters of pressure of mercury. There is a flow restrictor, which gives 4 ml per hour. Then another thing it gives here the monitor. First normal saline at 300 millimeters mercury flow restrictor, 4 ml. Catheter 20 to 22 gauge parallel sites. PMO lines less compliance to decrease damage. Transducer, yes. The blood pressure pulsations are transmitted from the aortic canula up to the connecting tubing to the transducer. This relies on the hydraulic coupling. What is this? In nature of water. The pressure when you pass through the column, right? The transducer will receive the column and converts an electrical signal, or it is attached to the Wheatstone's bridge. What is it? This is the Wheatstone's bridge. Now the pressure is correct. This is changed. The resistance wire is changed. Yes. Now I'll go again to this. When the transducer diaphragm moves, already there is a current here. You see here there is already current. When the transducer moves because of the pressure, The sensitivity can be described as a change in the applied current. Okay. Now, there is a 5 microvolt meter per millimeter of mercury. Here, the transducer gives the resistance is differed, and there is a change in current. This voltage is micro per millimeter of mercury. 5 microvolt. No, there is a confusion. Is it really a transducer? Because this is a transducer. You have an hydroelectric power. Where to run? Water is falling and it changes into current. This is a windmill. The windmill is circling. The changes into current. Mechanical energy is converted into electrical energy. The transducer is not like this. What we use. There is already a current. Okay. It doesn't transform your mechanical energy into current energy. So it is not a pakka transducer. What it does is, it causes a change in the resistance of the resistance bridge so that there is a current change, voltage change, which is 5 microvolt per millimeter displayed in the monitor. There is an alternator. Resistance changes in the circuit. Galvanometer shows the current, and this is calibrated as BP. Now we have a measurement of invasive lines. If you have a central aorta, it is like this. Brachial, it is like this. Radial, it is like this. One dorsal is pedicellary. This is called systolic amplification as it goes to the periphery. Systolic amplification as it goes to the periphery. Now the normal wave is anacrotic limb, dicrotic notch, dicrotic limb, like this. This is difference is transverse. This is the systolic pressure and this is the diastolic pressure. Systolic pressure is 115, diastolic is 80, the pulse pressure is 35. And this mean arterial is calculated by area plus base, that is 97, base plus area. Now we have a rate of stroke, peak systolic pressure, dicrotic notch, then there is a diastolic pressure, and this is the pulse pressure. This is the area A, B. Now we have already told in the aorta it is like this. In the dorsalis pedis it is like this. Systolic pulse amplification. The diastolic comes down like this. The pulse pressure slightly rises. Okay. Now we can see in the dorsalis pedis. It is like this. There may not be even dicrotic notch now. Now you can see one more here. This is a, see here. This is 114 by 16 and this is 126 by 16. This is what we have flushed. After the flush, sometimes what happens in damping, I will come back. This is very interesting case. Now we can see the next. Now we don't know what is happening. The BP is coming down and see, you can see here. Femoral line is minimally tight kink. Now I show what is resonance. Resonance is a phenomena in which an external force or frequency causes the system to oscillate at greater amplitude. Now the system is oscillating like this, okay? An amplitude and at a frequency. Now you see amplitude is 1 centimeter and frequency is 20 hertz. We'll keep like this. 20 hertz it is doing or 2 hertz like this and 1 centimeter. Okay, is the amplitude. Now if you are giving one more external force where the frequency is same 2 hertz, then this will cause this thing to lie like this. So that is what is called the resonance frequency. 5, 10, or 50 external frequencies are fine. One more example. For example, now if you are in a bridge, you can see in the army, people are not put like this in a bridge. For example, this is oscillating in some frequency, and you are putting some more. If the frequency of that foot equals the frequency of the wooden bridge, then the wooden bridge will do like this and throw the currents out in this. This is what is called resonant frequency. In clinical practice, resonance occurs when the frequency of the arterial waveform approaches the natural frequency of the IVP. Now your invasive monitoring system like IV fluids, that all these things are having a natural resonant frequency. That frequency should not be equal to the radial artery frequency. If that is going to be there, the amplitude is high. Okay, that is one problem. So we need to keep. So 60 beats per minute is 1 hertz, 1 to 3 hertz. Normally, let us take the waves is 1 to 2 hertz or something like that. Now you have to keep your IV set, all these things. That frequency should be at least 10 hertz. If it is the frequency also is 1 hertz, your amplitude because there is a frequency, there is an amplitude. You are giving it one more external force, which frequency is similar or a resonant frequency, then the amplitude will go. That is what we have told, bridge is through the heart. So that is the problem. You have to keep as 10 to 30 hertz, your frequency of your tubings. If we have frequency of the systolic system very high, 30 hertz means sometimes the systolic amplification may be less, and you may see somewhat equal in dorsalis, femoral, and radial. There is something called second to jumping energy. Sometimes what you do is your weight is 48.5. Okay, your weight is 48.5. And what happens is if you jump into the weighing machine, it will show 65. And you just release it, will show 5. So it is not 55 and it is not 5. So you are creating an amplitude by giving an external frequency, which is equal to the resonant frequency. So thus to attain the highest possible in Nantart will be required short. So what are the things needed? Short tube, wider tube, stiff cannula, lower density of fluid. All these things are necessary to have a higher natural frequency of the system. The system there, if you have a long, short, narrow tube, then your frequency will be close. That is what we don't want. This is what is the problem. So you have to have a short, wider tube inside the arterial system. You have to have the PMO line, not extension wire. Now, what is damping? Damping is the magnitude of the difference between the input pressure and the transverse pressure. Now, there is pressure something, but there is some pressure. Something is causing decrease the pressure. That is what is called damping. Now, normal, over damp, under damp. See here, the same patient, it is over damp. You have some three ways, some blocks, under damp, three-way blocks, air bubbles, clots, additional length of tubings, kinking of tubings, all these will cause damping. Now you activate the fast pressure. Everyone knows not the red. With this fast square waveform will come. And after that, what happens? We should know. You fast pressure and leave it. Then what happens is only one will come like this. After that, the routine waveforms will come. This is the norm. If you have over-damped system, you will not get anything. See, the damping is there and it is immediately. If you have under-damped system, it will show 4 to 5 waves. And then when we come to the natural arterial waveform. The damping coefficient we need to have 0.6 or something. One means there is no oscillation, but the response time is slow. You need to have a response time fast. So the response time is minimal overshoot. This is what is needed. Damping coefficient of your system should be 0.6 to 0.7. Now we go to some clinical scenarios. Now this is the pulse. You have a waveform like this. Now the pulse pressure is the difference between systolic and diastolic. Here you can see the pulse pressure is 760 and here is 35. This is more than 50%. If the delta pulse pressure is more than 50%, then it is hypovolemia. Just see here, this pulse pressure here. Sometimes it may vary with respiration. All these things point out that there is hypovolemia. Sometimes you see damping an arterial line, rare causes. Microscopic here, clamped by the nurse partially. We need to zero the transducer. There is no pressure. Zeroing of scales before weighing. Let's see, 0 scale, you stand, it will not show. No, already the scale is showing 15. You stand up on it, you are 17, become 85. Something like that. Same zeroing is for arterial systems. Leveling with the phlebostatic axis, right? I have already described other video. Hydrostatic pressure on the readings. The phlebostatic axis is the fourth intercostal space in the mid-axilla. Relevant to supine up to degrees, everything should be clear. The transducer should not be level at the line of arterial catheter. Transducer should be at the level of hydratium and not your radial. Transducer should be at the level of phlebostatic axis and not at the level of arterial catheters. If the transducer is 10 centimeter below the level, BP is 7.5 millimeter higher. If the transducer is 10 centimeter higher, your BP is 7.5 millimeter lower. Now you see the hypertension. Here you can see the pulse pressure is 108. And note that narrow systolic tip here, and there is some reflection waves. Now you start this patient on nitroglycerin, your BP has come down. There is sometimes called as the NTG started. Another reflection wave will come. This is not a dichrotic notch. This is only the dichrotic notch. The reflection wave. This patient is in shock. Now this is very much damped. This here, the dichrotic notch, another reflection wave in the dichrotic phase after the dichrotic notch. Now D indicates dichrotic notch. This is the patient in shock. Now normal waveform, vasoconstricted, vasodilated, high contractility, low contractility. See this. Watch this again and get into the mind. Vasoconstricted, vasodilated, low contractility, high contractility. See the contractility here. See the contractility here. See a lot of blood clots here. You see blood clots, it is gone. Now you have to have a PMO line here, not the infusion line. This is extension line of IV. This is what is called the PMO line. This is less compliant. Now we have resonance, damping, zeroing, leveling, anacrotic notch, dichrotic waves, etc. Thank you very much.